In this video, we will discuss the alternating series. And looking at this first part, we'll skip over the exploration part and go straight to the test. So with the alternating series, notice you have your alternating signs occurring here, or it can occur like this. So that's going to converge if the following conditions are met. Notice each term is positive. It passes the nth term test, and notice that these are decreasing in value. So verbally speaking, again, the alternating in sign, decreasing in value, and notice it says magnitude, so it's talking about the absolute value, and then you have a limit of 0. So let's look at what that's going to look like. First, let's talk about a little bit of caution here. This does not say that if not equal than 0, that the series diverges by the alternating series test. That alternating series test can only be used to prove convergence, not divergence. That's going to be your nth term test. So be careful with that. The wording there is very important. So we're going to check out some problems, and we need to determine whether or not this series will converge or not. And so let's look at some of the terms, and let's go back and review what each part of the alternating series test consisted of. Remember, the first thing, you had to alternate signs, so you have to make sure that happens. And so looking at this, boom, that's going to happen right there. And then the second thing is we are decreasing, so we have to decrease in magnitude. So that's your absolute value. Remember, magnitude is going to be absolute value. And then the third thing is that you have a limit of 0. So the limit as n approaches infinity of our sequence must be equal to 0. So those three things must be met. So let's look at the first, and let's just list out some of the terms in our sequence to see what's happening with the series. So here we're going to start with a sub n. And again, we're looking at decreasing in magnitude. When we list these out, we see that we're alternating signs. So if I start plugging in at 1, and essentially with the magnitude, you're just going to ignore the alternating signs and just list out the magnitude of each term. If I plug in 2, I'm going to have a 4th. If I plug in 3, I'm going to have a 9th. And then 1/16. And we see very quickly that each term is decreasing in magnitude. And so here, let's see, as we're continuing on, we have our alternating signs. We are decreasing in magnitude. And look at our limit value. If I look at just the limit here, as n approaches infinity, of just 1 over n squared, because again, we're just looking at the limit for each one of these terms, then we see that does tend towards 0. So notice all of those conditions have been met. We see that we are decreasing, and we probably should list that as well. So we have our alternating signs, and from here, let's go ahead and add that the n plus first term is less than the nth term as n approaches infinity. So now we can state, therefore, this converges by the alternating series test. All right, so let's look at our next problem, part B. Again, we need to look at our 3 conditions. 1, do we have alternating signs? And as soon as we see that, that is true. 2, are we decreasing in magnitude? And then the third thing is that limit as n approaches infinity of that, oh my gracious, infinity of a sub n, does that tend towards 0? So now let's list out our terms and see if they are decreasing in magnitude. So here for a sub n, if I list out each one of those terms, and I'm going to start at 2. So we're going to have 2 squared over 2 cubed plus 1. And then if we go up to 3, 3 squared is 9 over 3 cubed, 27 plus 1, 28. We can even go out to 4 just to make sure. 16 over 4 cubed, 64 plus 1, 65, and so forth. So we see that the n plus 1 term is less than a sub n. It is decreasing. And if we look at the limit as n approaches infinity of our sequence, then we see that that does tend toward 0. So now we've met all of those conditions, so therefore this converges by the alternating series test. Okay, let's go look at some more examples. All right, so for our next one, we need to look and see what's going on with each term again, and we do need to remember that we have to be alternating signs. So again, that was our first. Are you alternating signs? And we see for this one we are. The second step with this is each term decreasing in magnitude. And then lastly, does our limit as n approaches infinity of the sequence, does that end up, or series, does that equal 0? So let's see. We do have alternating signs. Let's look at each individual term, and it looks like it probably would be decreasing. So we're going to have 1 over 2, and then 2 over 4, and then, let's see, 3 over 8. Because right here it did not decrease there. So I had a little bit of an issue with that. Oh dear. Let's plug in. Let's see, that was 1, 2, 3. Let's do 4 just for grin. So that's going to be 4 over 2 to the 4th, which is 16. So we see now that our n plus 1 term is less than our nth term. And then if we look at our limit as n approaches infinity of n over 2 to the n, or a sub n, either one, we see that have some interesting things going on with this. I believe this would tend towards 0 just because that bottom would be growing faster than the top, as the bottom is exponential. So therefore we can say that this does converge by the alternating series test. All right, let's look at part D. D looks very strange with this one. Goodness, how in the world? I don't want to list out all those terms for sure. So again, we are alternating. Well, to show that we're decreasing, let's list out some terms just to see. I'm not real thrilled with that. We're going to have natural log of 1 over 1, and then we would have natural log of 2 over 2, and then natural log of 3 over 3. So it's kind of hard to tell that this is decreasing. I would say that it is, although it looks really strange because you're going to have 0, and then we're going to go to 1/2 natural log 2, and then we're going to go 1/3 natural log 3. We need to put our 3 dots there. Oh dear. All right, so kind of hard to tell. So let's just pretend we've got a function here, because if I know that derivative is negative, then I know that my function is decreasing. So let's go back over here and say, well, let's suppose we have this function f of x, and that's equal to the natural log of x over x. So let's see what's going on with f prime. So we're going to have bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. And so f prime at x is going to be 1 minus natural log of x all over x squared. We need to know where the critical number is, so I'm going to need that derivative to be 0. And since that derivative is a fraction, I need to know where that numerator is going to be 0. And so if I add natural log x over just because it's negative, I'm going to see where natural log of x is 1, so x has to be equal to e because natural log of e is 1. So x equals e. So let's think about here, e is a critical number, and so I know at e, my derivative is 0. I know f prime is going to be 0 here. So I need to pick a smaller value and a bigger value to see what's going on each side. So I'm going to cheat. I'm going to say e squared. I'm going to let x be e squared. And if I'm going to do that, then I can come back here and see, well, what's going on? What is f prime of e squared? And that's going to be 1 minus the natural log of e squared all over e to the 4th. And I see real quick that that's going to be 1 minus 2, so that's going to be negative. So over here on the other side, we could say that's e to the 1/2. That's another good little cheat. So then that's going to end up f prime of negative 1, or f prime of 1/2. Well, that's going to be 1 minus natural log of e to the 1/2 over e to the 4th, and that's going to give me a positive value. That's going to be 1 minus 1/2 over e to the 4th. So I know it's positive over here. So now I see that, yeah, this is decreasing in value because over here past e, I am decreasing in value. So after we hit that critical point, we are decreasing. So we have shown that it is decreasing. My gracious. So here we are decreasing. The limit of the nth term here, we're going to see that does go out to 0. Okay, next we will talk about the alternating series estimation theorem. And we are going to go through the exploration of this. If you first look at what we're given, then we see that we are alternating and it converges absolutely. Then the sum of the series can be approximated. So now we're talking about the actual sum since this is converging. So the actual sum can be approximated by adding the values of the terms, with an error of the absolute value of the first unused term. So that sounds kind of complicated, but let's look at what that's implying. So let's see, we've got this here, the series, and notice how I have all of those strung out through there, and that sum is 0.828. So what would be our next unused term? So it looks like here this is going to be when n was 9. So my next unused term would be when n was 10. So that 10, we're going to have negative 1 to the 10 plus 1. So that's odd, so I know it's going to be negative. So I'm going to have negative 1 over 100. So that is the next unused term. So what this is telling us is that our error in your estimation, or the error of the sum, has got to be less than what the next unused term is, and that is going to be 1 over 100 whenever you look at the magnitude of it. So, or you can look at that as point, which is about, or no, it's not, it is exactly, goodness, that is exactly 0.01. So if we use our calculator and find the first sum of the first 200 terms, then if we do that, we're going to end up with 0.822455. if we go through and we find the sum of the first 200 terms. So what is the error in our estimation? Well, that's going to be the very next term. That's going to be here. If we look at the next one, that's really the absolute value of the 201st term. That's going to be that error approximation. So if we look at that, then that's going to mean that I have the absolute value of -1 raised to the 202, because it's n plus 1, over n squared, which is going to be 201 squared. That's going to be the error of my approximation. And so that's going to be approximately, once you plug that in, your calculator, 0.000025. So it's going to be your next unused term. And of course, it is the absolute value of that. Okay, so let's try another problem with this. We are going to approximate the sum of S of the series by using its first 4 terms. So now we are approximating using the first 4 terms. So let's list out those. So our sum is going to be about, and if I start listing out, we're going to plug in 1. So that's going to be 1 over 1 factorial plus, and if I plug in 2, notice that it's 2 minus 1. So that means we're going to have a negative. And so that's really going to turn into, let's see, -1 over 2 factorial. If I plug in 3, that's going to be positive. So we're going to have plus 1 over 3 factorial. And notice we needed first 4 terms. So we've got 1, 2, 3, and now let's do our fourth. So minus 1 over 4 factorial. And if we go through and put all that in our calculators, we're going to end up with 0.625. Right? So now we need to explain why the estimation found in A differs from the actual value by less than 1 over 100. So let's look and see. Now we have to make sure we do converge by the alternating series test. So let's go through and make sure. 1, we have the signs are alternating. So we do have alternating signs. Okay, when we look at the magnitude, we see that the a sub n plus 1 term is less than a sub n. And again, that's in magnitude. So you're looking at the absolute value of it. And then notice that the limit, if we look at the limit as n approaches infinity of 1 over, it would just be 1 over n factorial, that's definitely going to tend towards 0. So we know that this does converge by, so all of that being said, this converges by the alternating series test. Okay, so now that we have that established, now we can talk about how that our estimate is only going to differ by less than 1 over 100. So our remainder is going to be our 5th term. So what that actually looks like is, and again, all of this is in magnitude. So we're going to take the actual sum of the series because we're trying to show that the difference is by less than 1 over 100. So I take the actual sum, whatever that is, and I'm going to subtract out of that the partial sum of the first 4 terms. I want that to be less than the magnitude of the 5th partial term, or the 5th term, not 5th partial sum, my gracious, of the 5th term. All right, so how in the world are we going to show that? Well, we need to talk about, well, what is the actual 5th term? So that 5th term that we have, we're going to plug in a 5, And that's going to give us 1 over 5 factorial. So our fifth term is going to be 1 over 5 factorial, which is 1 over 120. So I've got to show this is less than or just less than 1 over 120. And so let's see, that is actually, there's that fifth term. Well, we see that this part here, that actual sum is going to be. And if we go back to what the alternating series estimation tells us, is that if a series is alternating and converges, then the sum of the series can be approximated by adding the values of the terms. And here's the thing, with an error of the absolute value of the first unused term. So the error within the error, so the absolute value of the error, E-R-R-O-R, my goodness, of the absolute value of the first unused term. So here's the first unused term. So that error then would have to be equal to or less than 1 over 120. And so that tells me here that that 1 over 120, and I can just continue that on, that is going to be less than 1 over 100. So again, all of this, you have to go back up and look at what it tells you about the alternating series test. It's telling you again that the sum of the series can be approximated by adding the values of the terms with an error of the absolute value of the first unused term. So the key to this, after you go through and look at it, go find that first unused term. The absolute value of that is going to give you a great idea of what your value should be. Okay, now we can look at one more way that we can classify a series, and we're going to talk about absolute and conditional convergence. So it is important that you remember what each one of those would imply. A series is called absolutely convergent if the series of the absolute values is convergent. If a series is absolutely convergent, then it is convergent. A series is called conditionally convergent if this series converges, but notice the absolute value is not convergent. So you have an absolute convergent, that's where the original and the absolute value of each term, both of those do converge. However, you have a conditionally convergent if the series converges, but the absolute value of its terms do not converge. All right. Okay, in our next examples, we're going to look at some classic examples of where we have an absolute convergent or a conditionally convergent. And you will see this on that AP exam somewhere, somehow. So looking at our first, if we talk about just our alternating series, keep in mind we can look and see the first thing. We do have alternating signs. That does occur. We have that here. The second thing that we have, we need to make sure our a sub n plus 1 term is less than our a sub n term, and that's in magnitude. And if we look at our terms, notice if we plug in 1, we're going to have 1. If we look at, and again, we're looking at, remind ourselves, we look at the magnitude, so we're going to ignore the alternating signs. And so that would be a 1, and then if I plug in 2, I get a half. If I plug in 3, I get a third, and so forth. So we do see that is true, and that is true. And then the third thing, if we look at our limit, as n approaches infinity of 1 over n, that does tend towards 0 as well. So we see that this part here does converge by the alternating series test. Now, that is alternating series test. Now we need to look at whether or not we are conditionally or absolutely convergent. So to do that, then we have to look at the absolute value of our series. In other words, if we look at that, then we're going to look at here as n equals 1 to infinity of 1 over n. If I look at without the sign changing, if I look at that part there, well, we see that that is harmonic series and this diverges. So notice that this is going to be conditionally convergent. So, and again, we see that because if I do the absolute value, in other words, I just look at the series as it is without the alternating signs, then this is conditionally convergent. Okay, so let's look at our next one. And I think we can look at this one pretty quickly until we're really going to relate that back to 1 over n squared, because we are taking out the absolute, or taking out the alternating signs. So first, let's go ahead and make sure this does converge by the alternating series test. We do have alternating signs, so the second part, let's look at some terms. So the terms here, we would have 1, and then another term we would have 1 over 4, and then the next term we would have 1 over 9, and so forth. So we see that the n plus 1 term is definitely smaller than the nth term, a sub n. And then the third thing, if we look at the limit, as n approaches infinity of 1 over n squared, we see that does tend towards 0. So here we do have convergence. Now, if we look at our series from 1 to infinity of just 1 over n squared, we see that this also converges by the p series. So that's important. Make sure you know how you know that that does converge, and you know the p series, that's our exponent there is greater than 1. So this one, notice that the absolute value and the series itself both converge, so this would be an absolute convergence. Okay, let's look at a couple more. For our next one here, we do need to check everything out, see what's going on with this one. We do have an alternating sign, and this one sure does look like it. We are multiplying by this each time, so I believe this is going to be a geometric. So here again, this is geometric. So it's not you do have alternating signs. We do have geometric. And so let's look. I think we're going to have both of these to converge, because if we go back and look at our alternating series, then we do see that our conditions are met. Here we do have positive terms. Our limit, let's just go backwards here. Let's look at our limit as n approaches infinity of 0.01 raised to the nth. That is going to tend to head towards 0. The n plus first term is less than the a sub n term. We do have positive. We do have all of those nice, neat positive. The signs are alternating here. So we have all of those different things going on. And so we see that by the alternating series test, we do converge. And then if we go back and we look without the signs, then we have that geometric series we noticed earlier. So we also see that here, again, if we're just looking at 0.01 to the nth, and n is 1 to infinity, that is geometric, and so that also converges. So they're both convergent. So this, again, is an absolute convergence. Our next example, Now the cosine of pi n looks strange, but think about what these values are for n. That's going to be cosine of pi, and cosine of pi is -1. Then cosine of 2 pi, that's +1. So back and forth, this is just giving us alternating signs. So don't let that notation fool you. That's all that's noting is alternating signs. So we are looking at here, it does alternate. We have 1 over n squared. And so that is going to be a p series. And p is greater than 1, so this converges. And then if we look at, we do have positive here terms. We are a sub n plus 1 is certainly less than a sub n. And then our limit, as n approaches infinity of 1 over n squared, that does go out to 0. So notice both of these do converge, and so this does converge absolutely or absolutely convergent.